Hi, folks. We've got a couple quick segments about the first half or so of chapter 17. I've written the notes out already, and I'll narrate them. So I'm going to narrate them a little bit quickly. I strongly encourage you to go back over these at least once, if not more times, to sort of slowly, sort of step by step, to make sure that it all lines up for you. First, I'm going to ask you to remember gravity. We've got Newton's law of gravitation, that the force between two masses, let's call them M1 and M2 for now, is the product of the two masses times the universal gravitational constant divided by the distance between them squared. Looks familiar at this point. Remember also that we defined the potential energy due to gravity as mgh. Now, with a little bit more calculus than I want to go into, we can demonstrate this result. But I've got a sort of a conceptual argument to justify it. Mg, that's the weight of an object with mass m, subject to an acceleration due to gravity, g. But that's the force exerted on that object by gravity. Well, that's this. So I'm going to replace the force exerted by gravity with what Newton's law of gravitation tells me that it's equal to. G m1 m2 over r squared times h. Now, here we've got our two masses, m1 and m2. R, in Newton's law of gravitation, is the distance between the centers of mass of the two objects. H is the height above the surface, right? Like mgh was the height above the surface of the earth, or the height above wherever you put zero at any rate. But if m1 starts to look less like the entire Earth and more like a point mass, and when I mention point mass, I want you to think about point charge as well to kind of tie into everything that we've been talking about a little bit. The more m1 looks like a point, the more the distance between the centers starts to look like the height above the surface of m1. R starts to look like h. And if R is about equal to h, then we can cancel them and end up with a single factor of R in the denominator. Now, so far, we've got this. But the farther away from M1 we get, right, the higher our elevation above the surface of the Earth, the greater we expect our potential energy to be. But that's not how this function behaves. Increase R, this function decreases. That's not what we want. As we get farther away, we want to have more potential energy. We let go and we can fall more. Okay. As R increases, we expect potential energy to increase. So let's keep this dependence, make sure that it does vary like 1 over R. But let's set the floor for potential energy as infinitely far away. think about the Earth and the moon or a spaceship. In order to actually escape Earth's gravity, we have to be infinitely far away. Infinitely far away is where, if you released an object from rest, nothing would happen because it's too far away from whatever M1 is to be accelerated towards it. That we have no potential energy because we can't fall from infinitely far away. We aren't trapped anymore. And that's the thing. When R is infinite, the potential energy is zero because we don't fall. We're too far away to be attracted. Otherwise, if we're any closer than that, we're trapped by the gravity of M1. Eventually, we will fall. And we are stuck in the gravity, the gravity effect of M1. In order to pull ourselves out of the trap of the potential energy hole that we kind of find ourselves in, we would have to do work. We would have to put energy in to overcome the fact that we're stuck in the gravity trap. So I'm going to argue that it makes sense to set 0 as infinitely far away and set the potential energy value to negative when we're closer. If we do that, the closer we get, R decreases. A smaller denominator means a greater fraction, but it's negative. So we've got a larger magnitude, negative number. We start really far away, we have 0. We get a little bit closer, now we have -1. We get a little bit closer, now we have -2. We get much closer, now we have -3,000. We get really close, now we have really large negative. The closer we get, the less our potential energy becomes. The closer we get, the stronger gravity is. The deeper the potential energy hole, potential energy well that we have fallen into, right? The stronger the trap, the closer we get to M1. Okay, so go the other way. The farther away we get, the less and less negative this becomes. That's an increase, right? Starting from very negative and going to less negative, that's increasing, which is what we expect. Okay. We could ask ourselves, how much potential energy does M2 have per unit of its mass as a result of living in the gravity of M1? All right. The potential energy that M2 has divided by its mass. All right, so we take this formula, divide by M2, so that it cancels this one, and we end up with this. That M1 creates a gravity environment around itself that means that other masses are bound, trapped by their potential energy in that environment, in that configuration, wherever we put them, that M2 has a negative gravitational potential energy because it is attracted to M1. The minus sign handles the attraction. M1, the bigger the mass, the stronger the gravity. And then the 1 over R dependence, the farther away we get, the less and less negative this becomes. The less strongly bound is M2 by the gravitational effect of M1. Okay. I'm going to pause the recording, change a couple letters, and say this all again. Ta-da. Instead of gravity, let's think about the Coulomb force. So we're talking about F, so electrostatic, not gravitational anymore. Replace capital G with K, replace the masses with Q. Okay, not really sure what to do with this. I'll come back to it. But let's keep replacing capital G with K and the masses with Q. So instead of G M1 M2 over R squared, now we've got K Q1 Q2 over R squared. The same story works here, that R, the distance between the charges, and H, the height above the charge, are closer and closer to being the same, the smaller the charges are. So we can cancel R with H and end up with this. Now, this was when we put in the minus sign for gravity. But the trick with gravity is that mass was always positive, and we needed a way to talk about the attraction that one mass feels for another. Here, the attraction or repulsion is built in. If Q1 and Q2 are the same sign, then we've got a repulsive effect, right? Oh, I should have changed these. If Q1 is positive, and Q2 is also positive, then they push each other away. That's the second case. It's not a trap anymore. Q2 is running away. We've got to apply forces to keep it where it is because Q1 is trying to push it away. It's not trapped. It's like escaping. If we started with Q2 over here, we would have to do work to push it to this point because Q1 is trying to push it away. If Q1 and Q2 are of opposite sign, then the product is going to be negative. And that means attraction, just like we saw when we talked about gravity. If the resulting product here is negative, that means the potential energy, not due to gravity, but due to the electrostatic interaction, is negative. And that's a trapped state, just like we saw before. In either case, whatever the story is, the farther away we get, the less the interaction matters because the weaker the force gets. So the farther away we get, the less the size of our potential energy. The repulsive case is a little bit different. Instead of taking one mass and moving it a height above the other, think of it more like pushing a mass uphill. The farther uphill, the closer we get to the top of the hill, the greater our potential energy becomes. When we let go, that energy gets converted into potential and we get pushed away. Pushed away from the positive charge, if we are also positive. We roll downhill away from the top of the hill. Just like the rubber duck that we talked about in Tuesday's class gets pushed away from the water coming into the tub from the faucet. That water coming in pushes the duck away. And this is the same sort of deal. So the attractive case is just like gravity. Same story. The repulsive case is a little bit different. Requires us to tweak the metaphor just a little bit. Imagine that we have to push Q2 closer to Q1. We have to do work to move this object up the electricity hill, if that makes any sense. When we let go, it's going to roll back downhill. That potential energy that we added by pushing them closer is going to be converted to kinetic because Q1 is going to push on Q2, send it back this way. Either way, we can still ask a question about how much potential energy per unit of its charge Q2 has. We asked about it for mass a second ago. How much potential energy does Q2 have per unit of its charge as a result of being in the electric field created by Q1? And the logic goes the same way. We take our potential energy formula, we divide by Q2, and we end up with that. This ratio, potential energy per unit charge, I'd like to give that a name. I'd like to make a definition. So I'm going to use an equal sign with 3 lines, which means is defined to be. It's not equal for any other reason than we say so. The symbol I'd like to use for electric potential is a capital V. A capital V because another name for electric potential is voltage. And the unit joules of potential energy per coulomb of charge is defined to be a volt. named, it's the last name of the scientist, Volta, who first formulated an electrochemical battery by stacking multiple oxidation reactions on top of each other. Not one cell of reaction, but multiple cells stacked, a whole battery of cells. So he invented the battery. And we named the unit of electric potential after him. Okay, I said I would come back to this. I have to erase some things. Give me a second. The potential energy. We used to ask about the potential energy of a mass m subject to a gravitational acceleration g. So when we're talking about electricity, we're talking about the potential energy of a charge q subject to a electrostatic strength. How strong is gravity? G strong. How strong is the electric interaction? Electric field strong. Check it out. G, the magnitude of the acceleration due to gravity. We calculated 9.8 meters per second squared using the mass and the radius of the Earth. This expression is the force of gravity per unit mass. We divide by mass. The strength of gravity is the force of gravity per unit mass. The strength of the electrostatic force is the electrostatic force per unit charge. That's electric field. H was a distance above the floor, wherever the zero of potential energy was for the given problem. So I'm just going to talk about a distance d, some distance that we are away from a zero of potential energy. Ah. There's more. We asked about the potential energy per unit charge. Per unit charge of this charge, that's living in an electric environment, E, created by some other charge. But we said this ratio was voltage. Electric potential, V. So we just found another way to talk about electric potential. As the product of the electric field and the distance that we've traveled through it. We could have done the same thing with gravity. Called GH, the gravitational environment created by mass nearby. Call it the gravitational potential. Not energy, just gravitational potential. GH ED. Strength of the gravity field times where we are. Strength of the electric field times where we are. One more piece. Well, yeah, maybe two more pieces. Back in Physics 201, we defined the change in potential energy of an object in a configuration as the negative of the work done by a conservative force during some sort of move. We could do the same thing here. Let's talk about the change in the electric potential energy. Because we moved. Let's just say we're moving a charge Q in a constant electric field E for now. Instead of a position, we moved some distance, right? Should be equal to the negative of the work done by the electric field. Just like the change in potential energy of gravity was equal to the negative of the work done by gravity. So the change in the electric potential energy should be the negative of the work done by the electric field, by the electric force of the environment. there's a bunch of cool things that happen now. ED, we said, was V. So if we're changing where we are, we're changing ED. That means we're changing electric potential. Multiply by Q, move the minus sign, and we know how much work the electric field is doing. This expression makes a lot of sense. I'm going to write it again. Negative sign from over here. QE to X. Wait a minute. If we move further away from the source of an electric field, the size of our potential energy should decrease. Well, I'm worried about this minus sign. Hang on, I gotta fix this. Give me 1 second. QE, that's force. And this is why I'm nervous. The electric force, the electrostatic force, times the displacement should just be the work done, not the negative of the work done. So I gotta, hang on. I think I need to change something. Potential energy equals mgh, strictly speaking, isn't super well defined. Because h above what? I mean, it varies depending on the problem and what we're trying to do. What's really true is that changes in potential energy are related to changes in height. Because then it doesn't matter where the floor is. If we go from here to here, our potential energy changes by an amount, never mind whether I'm counting the floor as the floor I'm standing on or the surface of the earth, a story of the house below. So this is only accurate like this is accurate. What's really true is the delta. Changes in electric potential energy are as a result of changes in configuration, just like for gravity. So I'm going to erase this. It was a nice springboard, and it got us to this. But we don't need it anymore. And here's the trouble. This is if the electric field, the environment that we're putting Q into, if the electric field is positive, in other words, due to a positive charge, pushes a positive Q away, right? If we drop Q somewhere in the electric field E that it gets pushed away, it has a bunch of potential energy. As the electric field pushes it, that energy is converted into kinetic because now it's being pushed. It has a velocity. That kinetic energy came from the potential energy that it had, and as it's pushed away, its potential energy has to decrease. As it's moving away, the displacement and the electric field are parallel. The electric field points away, and so does the displacement, because that's the way it's going. But we need the potential energy to decrease. However, if we turn it around, if we somehow cause a positive charge Q to come closer to a positive charge creating an electric field that would push it away, if we get that charge to come closer, we need the potential energy to increase. It matters which way we are going relative to the electric field. The electric field always is pointing according to the charge that's making it. And whether if we walk away in that direction, our potential energy should decrease. If we walk towards, our potential energy should increase. The trouble is, both of those things are vector. If they are parallel, the angle between them is 0. And it's Q times E times displacement times cosine of 0. We would end up with a positive product, but we said delta PE needs to be negative. This minus sign needs to be here. If E and the displacement are anti-parallel, the angle between them is 180. And cosine of 180 is -1. That -1 will cancel this negative, and delta PE will be positive. Whew. Tricky stuff. It's still true that the change in the potential energy should be the negative of the work done. So the work done by the electric field, right? As we push that positive charge closer and closer and closer to the positive charge making the field, we are doing positive work, but the electric field is trying to push it away. The displacement is opposite that. The electric field needs to be doing negative work while the potential energy is increasing. Just like gravity, we push an object uphill, we are doing positive work, but gravity is doing negative work because the object is moving opposite the way gravity wants it to go. So this minus sign is perfectly good. It needs to stay. And that means that oh dear. Well, now, because this minus sign and this minus sign cancel. The missing piece. I said before that the electric potential was equal to ED. Again, that D is a little bit strange, and frankly, electric potential uh, above zero. I'm a little bit nervous. Suppose we are nearby a positive conducting sheet like we talked about in class today. The electric field points away. And the farther away from it we get, the less that field is able to push us. The less potential energy we would have released from rest, the less we would accelerate away because the weaker the effect. So as the electric field pushes us away, our potential energy should decrease, and therefore our potential energy per unit charge should decrease as well. Oh, I think, yeah. We've got the same problem with this directionality thing. If we're going away, the potential energy should decrease. So should the electric potential. So should the voltage. And I think we can fix it the same way, negative E dot delta X. Negative ED in a certain sense. As we walk through a displacement D, how is it oriented with respect to the field? This isn't great, but the minus sign is important here. Are we walking away? E dot D is positive, but we need the potential to decrease. Are we walking towards? E dot delta X is negative because opposite directions. But we need the electric potential to increase because we're getting closer and closer to a thing that is trying to push us away. And if we were released from rest, we would get pushed away more the closer we get. Negative Q delta V. This makes way better agreement with the definition of work at all. QE is the electric force acting on charge Q because of the electric field E. So this looks like F E dot displacement, which is exactly what we expect for the work done by a force. That's our definition, the force dot the displacement. So this lines up. Had to fix that minus.